Hello, and welcome to my presentation on the Nobel Prize awarded in physics in 1980. The award was awarded to James Watson Cronin and Logsdon Fitch for the discovery of violations of fundamental symmetry principles in the decay of neutral K-mesons. So, before diving into the topic, I would like to introduce a question. Matter of fact, a huge question in the fields of physics. As we all know, with the Big Bang, the universe was created out of energy and produced exactly equal amounts of matter and antimatter. But nowadays, we mainly see matter in the universe, but no antimatter. So the question arises, why is there this imbalance in the universe? And physicists have thought about it since ages, and my presentation is going to be on CP violation, which is a big building block in trying to answer this very question. So now let me introduce baryogenesis and the Sakharov conditions before getting into the topic of CP violation. So baryogenesis refers to the physical process that is believed to have occurred in the early universe. Its purpose was to generate baryonic asymmetry. So in other words, it's the discrepancy between matter and antimatter in the universe. Matter, which are the baryons, and antimatter, which are the antibaryons. So then Andrei Sakharov proposed a set of three conditions in 1967, which are necessary for an interaction to generate baryons at a different rate than antibaryons, which then would, in consequence, explain why we have more baryons than antibaryons in the universe. These conditions were influenced by the discoveries of cosmic background radiation and CP violation in the neutral K system, which is going to be today's topic. The three conditions, known as the Sakharov conditions, include interactions out of thermal equilibrium, baryon number violation, and C and CP violation. So, as mentioned at the beginning of the presentation, this Nobel Prize was awarded to two physicists, matter of fact, two American physicists known as James Watson Cronin and Logsdon Fitch. Continuing on with the discovery of CP violation, I would like to introduce some theoretical background to be able to understand the processes in this discovery. So, important. Before diving into this topic, I would like to introduce the Standard Model. So the Standard Model is a theory that describes elementary particles and their interactions via three of the four fundamental forces. So you've got the electromagnetic interaction, the strong interaction, and the weak interaction. We are going to focus on the strong and the weak interaction. The strong interaction binds quarks together to form protons and neutrons. They don't only form protons and neutrons, they form lots of particles composing of quarks, also kaons, which we're going to get into later. The weak interaction is responsible for processes such as beta decay, which is an important source of energy production in the sun. The weak interaction is important in this presentation because it's how our kaons are going to be decaying, in which way. So the particle interactions described by the exchange of field quanta, which are also known as gauge bosons, which are shown in red. For example, the photon is the field quantum of the electromagnetic interaction. Matter particles, which include quarks and leptons, are represented in green and purple. Antiparticles for both quarks and leptons exist, which have the same mass and lifetime as the corresponding particle, but opposite charge. These are not shown in the figure. Finally, gauge bosons are considered to be force carriers and have the spin of 1, which makes them subject to the Bose-Einstein statistics. So, let's go to the weak interaction. So it's very important to understand the weak interaction for this presentation. The weak interaction is one of the four fundamental forces of nature and is responsible for the decay of subatomic particles. So it is mediated by the exchange of the W+, the W-, and the Z0 bosons, which have a mass and are electrically charged. Well, except the Z boson, which is neutral. The weak interaction is unique, and in that it couples to all quarks and leptons, unlike the other fundamental forces, which have a more limited range of interactions. For example, the gluons, which I'm going to introduce later on. One of the most significant manifestations of the weak interaction is the beta decay, which is a type of radioactive decay that occurs when a neutron in an atomic nucleus decays into a proton, an electron, and an antineutron. We can see this very nicely here on the figure I've presented, where a neutron decays via weak interaction into a proton, the electron, anti-neutrino. So now coming to the strong interaction, where the gauge boson here is the gluon. Gluons themselves are also subject to the strong interaction and are responsible for the phenomenon known as confinement, which means that quarks are always bound together in combinations such as protons and neutrons and cannot exist as isolated particles. The strong interaction is responsible for most of the mass of ordinary matter, as well as the stability of atomic nuclei. In addition to binding quarks together in protons, gluons also play a crucial role in binding particles called kaons, which are going to be important for the presentation. Kaons are mesons composed of a quark and an antiquark, and they are subject to both the strong and weak interactions. They were first discovered in cosmic rays in the late 1940s, and they have since been studied extensively in particle physics experiments. So let's introduce the kaons. So the kaons are the lightest strange mesons, which means they are composed of a quark and an antiquark. In our case, they're the lightest strange mesons. So they're composed of a quark from the first generation, either up or down, and a strange quark. This is important. They are not the lightest mesons, which are the pions, which I'm going to introduce later on. Additionally, the three masses of the different kaon eigenstates are not equal, leading to their decay into other particles such as pions and muons. The decay of kaons played a crucial role in the discovery of CP violation, which helped to confirm the existence of a third necessary condition for baryogenesis proposed by Andrei Sakharov, as mentioned before. So let's go to the pions. In figure 5, we see a pion, a plus pion, which is composed of an up and anti-down quark. As mentioned before, the pions are the lightest mesons, composed of solely an up and down quarks, and exhibit additional decay modes. Important to remember is that all pions have a CP eigenvalue of -1. So now that we've laid a little bit of a basis, I would like to introduce the parity and the charge conjugate operator. So give you a little bit of a mathematical background to understand CP violation. So kaons are pseudoscalar particles. That is, they pick up a negative sign when we apply a parity operator, as we can see in the first line. The charge conjugation changes particles into their antiparticles. So the K plus goes to K minus, and the neutral kaon goes to the anti-neutral kaon, and vice versa. As we can see in the second line, it flips the signs for the charged kaons, and for the neutral kaons, it turns a kaon into an anti-kaon. So now we'll combine the two operators we just saw to give you the CP operator. But it should be noted that the kaons, as described by their quark structure, are not CP eigenstates. For an eigenvalue equation, the state has to appear on both sides of the equation, as we can see above, and as you probably know already from your linear algebra 2 class. So we define a new state K1 as the difference between K0 and anti-K0, so the anti-kaon, anti-neutral kaon, and a CP transformation exchanges the neutral kaon with its antiparticle while picking up a negative sign because of the parity operator, resulting in K1, which is an eigenstate. A similar calculation for K2 shows that it is also an eigenstate, but with a negative eigenvalue. I've put the equations below with the respective transformations, and we can see that the only thing that changes is the eigenvalue for the K2. Now, let's take everything we know and put it together and make some theoretical assumptions, or at least make the theoretical assumptions that have been made in the past. So the neutral kaons are known to mainly decay via weak interactions into 2 or 3 pions. It is noteworthy that each pion has a CP eigenvalue of -1, as mentioned before. Assuming that weak interactions remain invariant under CP transformation, the CP eigenvalue remains unchanged during weak decay, which would mean there is no violation. Consequently, the K1 decays into 2 pions and the K2 only into 3, leading the same CP eigenvalue on both sides of the equation. Therefore, K1 and K2 are considered to be CP eigenstates. So this is a theoretical assumption. Let's see what has been discovered experimentally. Now, experimental observations have shown that the decay of neutral kaons mainly occur through weak interactions into 2 or 3 pions. However, due to the similar mass of 3 pions to that of 1 kaon, the decay into 3 pions is less likely to happen, as it allows for only a small range of kinetic energy for the resulting pions. On the other hand, the decay into 2 pions allows a wider range of kinetic energy, making it more probable. I've thought about a little Gedanken experiment to try to visualize it to you, this phenomena. So imagine you're going on holidays and you always go with the same bag, and this bag represents the kaons. Now, you always bring jumpers with you, and the jumpers represent the pions. You will usually only bring 2 jumpers because you want extra space for other things. Now, once in a while, you will go on holidays to a very, very cold place, so you will bring 3 jumpers. But most of the time, you will bring 2. So, in analogy to our kaon decay, most of the times it will decay into 2 because it has more freedom, there's more kinetic energy for the 2 pions to decay. There's a wider range. Whereas when it decays into 3, this range is extremely small, so it's less probable. This results in the observation of 2 types of kaons in the experiments, namely the short-lived kaon, K short, and the long-lived kaon, K long, with the latter having a lifetime approximately 600 times longer than the former. The well-defined mass of the kaons can be inferred from their propagation in the lab, where the time evolution in quantum mechanics depends on an imaginary phase that is related to the mass. So up to this point, we've I've introduced 3 different basis systems. So we have the strong eigenstates, the CP eigenstates, and the mass eigenstates. And remember that the K1 and the K2 are distinguished by the number of pions they decay into. And we also know that a decay into 3 pions is not very likely to happen. So it makes sense to identify the K1 with the K short and the K2 with the K long, as I've displayed below or above. And so from there, this means that the K short and the K long must be CP eigenstates with the same eigenvalues as K1 and K2. Remember, this is in absence of CP violation. I've also displayed a graph to visualize it. In this graph, we have the decay short decaying into 2 pions, and the distance from production. And we can see it's a very it's a simplified graph, but it's a very steep curve, whereas then the decay into 3 pions is a very flat curve. The distance from production can also be related to the decay time, because if a particle takes longer to decay, it will travel further. So finally, let's go look at the experiment. In 1964, so 16 years before they received the Nobel Prize, Cronin and Fitch and other physicists conducted an experiment in which they allowed a neutral K-on beam to propagate in a long tube. As the K-long travels much further than the K-short, they obtained a nearly pure K-long beam upon reaching the detector. To their astonishment, they occasionally observed a decay into 2 pions. This implies that the K-long decayed into 2 pions and the CP eigenvalue on both sides of the decay did not match up. In this measurement, K-long mesons were produced at the Brockhaven alternating gradient synchrotron in an internal beryllium target bombardment by high-energy protons. The experimental setup illustrated in figure 7 is positioned relative to the beam. The detector, consisting of 2 spectrometers, each comprising 2 spark chambers separated by magnetic field. The spectrometers were positioned horizontally. The spark chambers were triggered via coincidence between the water Cherenkov and scintillation counters located immediately behind the spectrometers. So many of you might not know these detectors. I'm going to give you a brief overview of how they work. So I mentioned before the alternating gradient synchrotron, in short AGS, is a particle accelerator that uses the strong focusing principle to accelerate particles to high energies. At that time, the highest energies. This innovative design concept was developed by Brockhaven physicists and relies on magnetic fields to force particles onto circular trajectories, while electric fields are used to accelerate the particles. As mentioned before, spark chambers were used as detectors in this experiment. The spark chambers were used to visualize the tracks of charged particles. They consist of a sealed box filled with gas, such as helium or neon, and a stack of metal plates inside. So when a charged particle passes through the gas between the plates, it ionizes the gas, meaning the gas loses an electron, creating a trail of charged particles. A high voltage is applied between each adjacent pair of plates, which causes sparks to form along the trajectory of the charged particle. This makes the particles visible as a line of sparks. A separate detector is used to control when the high voltage is applied to prevent continuous discharging. Another very important device used in this experiment were scintillation counters. They are devices used to detect and measure ionizing radiation. They work by using a scintillating material that produces photons in response to incoming radiation. The photons are then detected by a sensitive photodetector such as a photomultiplier tube or photodiode, which converts the light into an electrical signal. The signal is then processed by electronics to determine the intensity and energy of the radiation. So, in addition to the scintillation counters, Cherenkov counters were used. But what are Cherenkov counters exactly, and what is Cherenkov radiation? Well, Cherenkov radiation is produced when a charged particle, such as an electron or a proton, moves through a transparent medium at a speed greater than the phase velocity of light in that medium. Not to be mistaken with the velocity of light, because particles can't travel at the velocity of light. But in a medium, they are able to surpass the speed of light in that medium. And by surpassing the speed, they will emit Cherenkov light. And how does this exactly work? So the emission of Cherenkov radiation is due to the polarization of the medium by the moving charged particle, causing a coherent wavefront to be emitted in the form of a cone. The radiation is categorized by its wavelength and intensity, which depend on the velocity of the particle and the refractive index of the medium. Cherenkov radiation is commonly used in particle detectors as in our experiment, such as in Cherenkov counters, which can detect and measure the velocity of charged particles. So let's have a look at the statistical analysis of Cronin and Fitch's experiment. So the experiment showed that about 1 K long in 500 decayed into 2 pions rather than 3 pions, so the wrong CP state. Hence, the CP symmetry was violated. Figure 3 shows the angular distribution of events with cosine theta greater than 0.995 in 3 mass ranges. One above the mass of the neutral K-meson, one below it, and one that includes the mass of the neutral K-meson, which is seen in the middle. The x-axis represents the cosine of the angle between the direction of the detected particle and the direction of the K-meson beam, while the y-axis represents the number of events. Now, keep in mind that in a 3-body decay, the angle theta is non-zero, whereas in a 2-body decay, the angle theta is 0. So they were able to limit themselves in this very narrow range. After subtracting the background, there were 45 plus minus 9 events observed in the forward peak out of a total of 22,700 K-meson decays in the corrected sample. So they were able to conclude, therefore, that the K long decayed into 2 pions with a branching ratio of about 2 plus minus 0.4 times 10 to the power of minus 3, where the error was a standard deviation. As mentioned, the statistical analysis was made in the 1960s, so it's quite in its basics, but it was still enough to show that CP was being violated, which was astonishing at the time. Now, there are 2 potential explanations for the CP violation. They are categorized as direct and indirect CP violation. So direct CP violation is to acknowledge that the K2 meson, also known as the K long meson, can undergo weak decay not only into 3 pions, but also into 2 pions. This outcome would breach the CP symmetry in weak interactions and is referred as the direct CP violation. This is because the K2 meson has a definite CP eigenvalue of -2, whereas 2 pions undoubtedly have a CP eigenvalue of +1, because it will be -1 to the power of 2. This is a so-called direct CP violation. So finally, let's have a look at the indirect CP violation. Another approach to studying CP violation is to redefine the propagating states of K long and K short to incorporate a small component of the other CP eigenstate, as seen in the first equation, where we have the K2 and the K1 eigenstate, but where the K1 eigenstate is multiplied by an epsilon, which is small. In this way, the K long can decay predominantly into 3 pions, but can also decay into 2 pions, but is no longer a CP eigenstate because one part transforms with a minus sign, while the other does not. For a process to be invariant under a transformation, both the initial and resulting states must behave the same under that transformation. However, this is not the case when one side is an eigenstate and the other is not. This is referred as the indirect CP violation. It has been discovered that CP violation occurs due to the mixing of K short and K long, as illustrated in the box plots below, rather than through the weak decay of the K long. According to the standard model, direct CP violation should exist to some extent in most weak decays. However, there is currently no conclusive evidence for a direct CP violation. So finally, I hope you enjoyed the presentation and that I was able to spark your interest in particle physics. The study of symmetry violation plays a significant role in the ongoing search for answers to the matter-antimatter imbalance to the universe, and there's still so much more to discover in this field. If you would like to gain deeper understanding of this topic, I highly recommend taking Nuclear Particle Physics 1 course, which has also been helpful to me in my own research. I would like to express my gratitude to Patrick Owen for his assistance and for his recommending further research papers. All references are listed in the following 2 pages. If you have any questions about the topic, please feel free to ask me below, and have a nice day.